Swayam Prabha. Digital India. Educated India.
Okay, so we'll get into some final topics. Ground shock is something we were not quite planning, but I do have a little bit of information about that. I can talk about it. We'll look this afternoon at one of the, if you want to do further things with, we've done some work with explosives inside casings with fragmentation. What are some of the issues? UFC does give you guidance, so we'll have a brief presentation on it. There's not going to be any problem or anything that I'll be solving. So there's a brief presentation on that, and then we'll show you some, if you're able to connect to the computer, how to use. The actual tutorial will be this afternoon, but I'd like to introduce you and expose you, if you have not yet used any of those, to what are the issues. We've said advanced analysis is, we always go to that as the final go-to, but always that need not be the answer, right answer. So we'll get at least introduced to some of those topics. So when you have ground shock, there are two types, either fully buried or simply, even in terms of the explosive being on the surface of the ground, and then you have the building at a distance of r. You have the air induced shock wave propagating, and then there is also, there is shock waves propagating in the ground due to this explosion. So this is what we say ground induced, and this is air induced. Now clearly what you have is, the medium is very different. So since the medium is different, the medium, there are two of them, basically air and ground. The transfer mechanism, basically this energy transfer. So the transfer mechanism is also different. So we start with, for instance, you could have phenomenon that occurs in the ground, for example, is something called cratering. So here you'll have crater formation. Directly underneath you have cratering, and cratering is also something you can calculate. I won't get into it today, but you can calculate the depth and depth of cratering due to charge weight. This can be calculated. So that effect is there. Then part of the energy gets transmitted, and I wanted to see if I can show you a brief video. So these are how in the ground, and if you've done seismic, if you're exposed to that, you would be aware of how these stress waves travel. Some of the resources, it's still UFC 340 has quite a bit of information regarding this. This is another document that you won't, it will be difficult to find. It may even be on request only. But what I wanted to show was, I hope the video works. So you see, one is in the ground, it's in the form of an S wave, just like a string. Right? So you apply force, and then it travels in the form of a string. So these are what are known as S waves, shear waves in some ways. And then, wait, let me, No, I wanted to start with this one. So, the first one is compression waves. These are like sound waves that you see. The compression waves, this is the direction of propagation direction is still the same, but you have a different mechanism of transfer. Then you have the S waves that you see. These are the two primary types of waves, and this occurs even in any seismic motion also. Then you have love waves. That is also, you see that it is in, it's three-dimensional, little bit on the sides as well. You see the direction of motion here is indicated by the pink arrow, particle motion. And finally, you have the Rayleigh waves. It's, you see the motion of the particle is circular in nature. Especially this occurs on the surface of the ground. And your actual waves is a combination of many of these. So, the principle that is applied as far as shock under the ground is concerned, you have these velocities of these particles that are moving, and the velocities of the particles, called particle velocities, PVs, they get transmitted to the structure that is here in the form of some pressures. So, that is the mechanisms of transfers. The other mechanism of transfer is you have accelerations. So, if your structure is at the end of it, you have accelerations at the foundation, and those, so let me get back to, so several mechanisms of transfer. Ultimately, we cannot separate them, and we combine all of them into, at least for analysis and design purposes, in something observable. But to understand it, one is you have the P waves. This is common to seismic, similar, I should say, and you have S waves, and then you have, so P waves is, as we have seen, motion this way, and sorry, the motion is in this manner, and S waves like a string, and then you have the love waves, which is transverse motion, and then finally the Rayleigh waves, which are circular in direction, especially on the surface. Now, so if this is your structure and these waves are hitting here, now from the reflection here, there is transmission of waves, any of these waves, and the ground, you apply them as a pressure. So, these have a particle velocity, and the particle velocity can be converted to a PSO value, especially for completely buried explosives. Whereas, if it is not a buried explosive, then you can have on the ground either acceleration as a function of time and or velocity as a function of time, and there are, once you have these, you can have displacements as a function of time as well. And then in these cases you can perform a seismic analysis, seismic type analysis. This is on the foundation, and so that from air induced you are going to have blast waves. So, on the surface you will have a blast wave, and ground induced you will have accelerations. These attenuate quite rapidly. Attenuate is they decrease. So, if the distance is too large, then those effects are not felt. But if the distance is close, you could consider, you can calculate some accelerations and decide based on how much g they are, whether to include those effects as well. What's that? So the ground waves, actually, it's a good point that you raise. You have the air, and then that's got a certain speed. At some point, even the ground waves can actually outrun the air effects. So you have the it's called the outrunning effect. But how that is considered in our structural design or any behavior of a structure, again we'll just that's the idea there. But you can find graphs where those two are going, and then you can see the outrun effect for the ground waves. So these are transient stress waves through the soil. So some of the characteristics are, these are transient. When I say transient, it is time dependent, but their effects is certainly not similar to what you saw yesterday in the form of shock waves. The greatest effect, of course, there is before that, let me mention, especially for buried, there is always a coupling between the ground and the explosive for partially or fully buried explosive. And the effect is the greatest for fully, there is, I'll talk about that also a little bit, greatest when charge is fully buried. Now, the energy from the explosive has two forms. The first one is the energy that is imparted to the ground, and the other is, this is what is called as direct induced ground shock. And secondly, you have the energy imparted through the air. This is air induced ground shock. We'll look at both of them. Just the characteristics. So for air induced ground shock, you have the following characteristics. Here the air blast compresses the ground surface. So that's the first phenomenon. The surface, and the stress travels through that, and itself then it's a pulse or a wave mechanism, and we are interested in the magnitude and the direction of the pulse. And this is applied as a side-on pressure on the, if it's a foundations and things like that. Clearly, it depends on the blast characteristic and the ground type, basically the soil type, because wave propagation is through the medium, as we've seen yesterday, the densities play a big role. And so the densities, so that comes into play. And of course, it is maximum at the ground surface and attenuates with depth. So if you have a parking garage that is in the basement, so in that case you should consider, so this is a good consideration for parking garages or other retaining wall type structures in the basement. So for that you could consider these. And if there are other mediums such as water bodies in between, all those things affect. Then if you look at now the direct induced ground shock, so here you have direct, what we call in seismic as direct ground motion is induced. One thing I want to mention here, it induces not just accelerations in the horizontal direction, these are vertical, but accelerations in the vertical direction also. In fact, even in seismic, I don't know if any of you have, I know any of you are working in seismic areas. For a long time, vertical ground accelerations were not considered at all. Even in US codes, horizontal ground accelerations, buildings were designed for that. So if you're going to shake something, there's going to be free vibration, so to speak, or damped vibration of the structure due to the motion. Now, vertical accelerations, they cause motion up and down. Only recently in the codes we have started incorporating, there have been advocates for that, and now you can see in ASCE 722 and maybe even the slightly earlier version, ground accelerations on certain types of structures. They don't affect all types of structures, but those types of structures have started coming into the code. And here we haven't done research to that extent, but that's something you can look at. And they have longer durations because they tend to be sinusoidal in nature. Any stress wave or any wave for that matter is sinusoidal, so then they tend to have clearly longer durations. So the net ground shock is essentially a complex combination of direct and indirect. So let's look at the relative magnitudes of the two. Of the two, they clearly vary. So first one, if the range or the R value close to the blast, then it is very high due to air blast, and you have a seismic wave velocity that we calculate. We'll look at that in the ground. And seismic wave speeds, so the wave speeds here are in the superseismic region. So just like we saw supersonic wave speeds yesterday in blast, Similar to that, you have in the seismic waves also, they have, in fact, you'll see the range is extremely wide. So this will be more in the wider region. Some of these things you can measure it and you can do, but for design purposes, you'll see that you'll have a wide variety to choose, a wide range to choose from. Then this is where the ground shock actually, let me see if I have a image of that. Did I take this one, or let's take this one. So the first one is, if you see the net ground motions produced by explosion on the ground surface. So you have the air induced, this is the motion of, and the direct induced is moving this way, and here this is the vertical velocity and the horizontal velocity. So they have both of them. And then the second one is the net ground motions. Again, this is figure 253. Here this is the vertical velocity and the horizontal velocity. These are air blast induced, and actually you can see the outrunning effect is what, as it is called out here, the air blast arrival, and this is the ground blast, the black, the solid one, and the lighter one is the dashed one is this is the dashed one, the air blast, and the ground one, as you can see, it's actually outrunning it. So you can look into that effect a little bit more. So let me also present that. I'll just put that here. Okay. So this is in the UFC 3-340 O2. So the combined motion of the two is by calculating the arrival time of each wave. So the TA, if that's your arrival time, for the air blast, you have the data for, this is the figures unconfined motions, and I'll give you several references from UFC. So this is unconfined explosion, the figure 215 2-7, and for the ground shock, the ground induced, you assume shock seismic velocities, and from that you can calculate, and the distances that you can calculate the arrival times. So let me give you some expressions that you can use for some calculations, and we'll take up an example. So for air induced ground shock, we use the one-dimensional wave theory. This is a longitudinal wave motion. So the P waves that you've seen, and then assume structure with uniform properties. So when you calculate equations, you assume the structure has uniform properties. So given these assumptions, the maximum vertical velocity is given as, this is the particle velocity. So, this is given as using the following expression. It is Vv is equal to Pso divided by rho multiplied by Cp. So, what are these variables? Cp is the compression wave seismic velocity, and I'll give you these references. This comes from table 2-11. All these references are from UFC 3-340. Then the rho is the mass density of the soil. So, this would be in pound second square by inches per 4. Your mass is weight by g divided by volume. So, inches per 4. This is table 210. This is 211. And then the third one is PSO, that you know is incident pressure. This is figure 2-15, right. So, that's your maximum velocity. Then you have your maximum vertical displacement. This is not quite needed, but if you are looking to calculate your displacements, you can use the displacement equation. dV, vertical displacement, is in terms of Is, applied impulse, rho 1000 multiplied by rho multiplied by Cp, and Cp is the compression wave speed. So, this is 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 the incident impulse. Again, figure 2-15. And finally, the maximum acceleration vertical, all of these are, remember, vertical. That expression is, it's a simple expression given as Av is equal to 1000 PSO divided by rho multiplied by Cp. Then for horizontal values, the same thing, it's taken as tan inverse of it. So, you are considering vertical and the horizontal. This is, let us say, dV and this is dH. So, the tangent, you will see that this is in the form of a tangent, and the angle is given as dV multiplied by tangent of sine inverse Cp by U. Same thing with the horizontal is V multiplied by tangent sine inverse Cp by U. I will come to the U part of it. And finally, the acceleration is also, just for the sake of completeness, it is the same expression, but sine inverse of Cp by U, where U is the shock front or velocity. given in, you can get this in figure 2-50. But for simplifications, if Cp divided by, this is unit conversions, 12,000 U is greater than 1, then the horizontal and vertical motions are similar to each other. All the values are approximately the same, can be considered that way. Now, what are the values? And I'll give you a few just to give you an idea of the ranges. If you look at, let's say, the type of soil and the seismic velocities, the mass density, once again the mass density is a little different from what you have seen, and the Cp is in inches per second. So if you see, for loose or dry soil, you have the density of 1.4 e power minus 4, and the range for Cp is from 7,200 to 39,600 inches per second. Another common soil is clay or wet soil. The densities are similar, at least in order, but the Cp values, as you can see, ranges is much more variable, much different from loose soil. Then you are getting into harder soils such as limestone, then the density is 2.25 e minus 4, and the numbers, I'm picking some extremes here to illustrate the variable. Yesterday Professor Aragappan was talking about, remember what was he talking about? Probabilistic determinations, right? Extreme values and ranges. So this helps you with establishing, if you're doing probabilistic type analysis, you can try to use these ranges to see where you stand. For compact, if you have coarse, it even goes higher, coarse or compact soil, you have to, this depends, but the numbers can go somewhere in between. Quite often you are in the middle. If you do not know what type of soil, this may be a good choice to go with, sort of the mid-range choice. And the other thing we do not know is what is the soil in between the explosive, and it's not going to be uniform soil. So we do not know, that's the case even with seismic. So you have again a lot of variability that I wanted to talk about. Now, coming to direct induced ground motion. So some of you have been talking about buried structures. If it is buried inside a compound or inside a tunnel type, you're going to have an air, and then the pressures are going to get energy is getting transmitted. So there is no direct contact of the explosive with the soil itself. Now here this is characterized for other types of soils, different types of soils. You can characterize it for dry soil, saturated soil, wet soil, clay, or rock. So for all this, if Z sub G is R sub G divided by W power 1 by 3, we have similar expressions for vertical motion. I'll take up a short example of this as well. This is the maximum displacement dV, and the expressions, as I mentioned, is characterized for different types of soils. So if you have rock, for instance, if in the case of rock this is given as 0.025 R sub G power 1 over 3 W power 1 over 3 divided by Z sub G power 1 over 3. And if it is for dry and saturated soils, the coefficient is different, 0.17 Rg power 1 over 3 W power 1 over 3 divided by Zg by, I'll check on this, this is 2 by 3. Let me make sure, I may have that in a presentation also. Let me make sure of that number. I don't think I have that here. This is yeah, I don't think I have. I'll just check on that, or we can check in. I don't want to give something that's wrong, so I'm going to just put a question mark here to be checked or confirmed. And dH is considered, you can take it to be equal to dV. What's that? Yeah, I have it as 2 by 3, but that's what I wanted to check. The maximum velocities for all ground types one thing I forgot to mention here, dH is dV divided by 2. Then the maximum velocities for all ground types is V sub V is 150 divided by Z sub G power 1.5, and the velocity horizontal is the vertical velocity, and finally the maximum acceleration AV is 10,000 divided by W power 1 by 3 Z sub G square. Which one? Which? Oh yeah, okay. So that is for rock. Let me just confirm that. This is for, you're right. So this is for so let's take this out. I'll show an example. So the acceleration, let's complete this. This is 10,000 and AH equal to AV by 2 for dry soil and AH equal to AV for wet soil and rock. What's that? So the acceleration was inches per second square. Same thing so let me, I have the a problem which we'll take up now. So what we are not doing out here is taking these values and using it for an analysis. So consider an example where you have W of 300 pounds of TNT and the R sub G is 50 feet. Question is to calculate the air induced and direct ground motion parameters. We'll get our PSO, Z and the impulse from figure 2-15. Z sub G is R by W power 1/3 comes to 7.47. Here and so from figure 2-15 you get PSO is equal to 17 PSI. I sub S is by cube root of W is 10. So I sub S is equal to 67 67 PSI pound millisecond, 67 pound millisecond. So those are the two values. Then we calculate the air induced ground shock parameters. Starting with the maximum velocity, V sub V is PSO divided by rho multiplied by Cp. Rho, let's say, is dry clay, which is 1 0.12 into 10 power minus 4, and Cp, as we have seen, varies from 30,000 to 75,600 inches per second. Say choose 50. Let me see if I've calculated for both. I've chosen 50,000, an intermediate value out here. So substituting, and if you look at 30, the other option of 30,000, lower end and at mid-range end, the values I get, V sub V is 17 psi divided by 1.12 into 10 power minus 4 pound second squared by inches per 4 multiplied by 50,000 inches per second gives us two values for VV. Just to get ideas about the numbers, in one case you get 5.6 inches per second. At a lower Cp, if the wave speed is lower in the system, we get the velocities to be 4.72 inches per second. This is for the same soil. It's, as we mentioned, it's again hard to pick, and so you can do probabilistic analysis in this case. The max displacement is dV, which is Is divided by 1000 rho Cp, which is 67 psi milliseconds by 1000 multiplied by 0.00012 multiplied by 50,000 inches per second. So comes to 0.012 inches, and it comes to 0.0186 inches for Cp is equal to 30,000. The displacement is higher. The third is what you will use for a seismic type analysis. So the maximum vertical and we have seen that the horizontal and the vertical accelerations for the Cp by 12,000 U. So the maximum vertical acceleration is AV, which is 100 PSO divided by rho Cp. So 100 multiplied by 17 divided by 0.00012 multiplied by 50,000. So AH is 303 inches per second square, and for the other case, for the 30,000 Cp, you get AH equal to 412. So if your structure is, you have a multi-story structure and you have foundations, then you will be performing a seismic type analysis. Say this is your multi-story structure or whatever building you have. You'll give AV here and AH and AV. and you can design. So in seismic design, even if you don't have your time histories, the structure is going to behave as though it's a multi-degree of freedom system. Say this is 3 stories, 1, 2, 3, 4. So let's say this is 4 stories. And if you have your AV for AH, for example, you're going to have what is known as an equivalent static, linear static analysis you can do. So these are the forces F1, inertial forces F2, F3. These are from seismic design principles. How are you going to combine? You now have forces due to the regular dead load, live load, wind loads. If you have regular seismic, normal E, and others also, rain, snow, roof live load, all these. So this is force 1, then due to blast, and then blast induced seismic. So in design, you perhaps, if I were, you'll calculate for each load case and combine load combinations. Do them separately. Although they are not occurring all at the same time, this is the only one of the logical procedures to combine all of them and design the structure for all these effects, because they are not synchronous, all of them, and it's difficult to really find what the actual forces are going to be at any given time. So this could be one of them, an approach. Then the last step is the direct induced ground motion. Considering for dry or saturated soil, dV is 0.17 Rg power 1/3, W power 1/3. This is 2.3. So, okay, that's confirmed. This is 2.3. What I had was correct. And dH is equal to dV. And 2.3. 2.3. Again, the parameters, these are not, as we said, you can calculate them, but what we use is the accelerations. Finally, you get AV, which is AH, which is 1000, this is inches per second, and W power 1/3 Zg square, this is 2.67. There is really a paucity of literature on many of these things. You have all these expressions and equations, and maybe there are very select, very few people actually deal with all these types of designs or even analysis, and it's hard to find anything even I've searched around and I've come up with some of my own interpretations also. Really, no books are going to talk about this much. There may be some examples in the UFCs. You can look into that. So, but this is just an idea on. Any questions? Yeah. Yeah. Surface burst cases. For buried, a ground shock, let me give you, I have a little bit more. I'll talk about that. Want to see if I can. So yesterday you saw that example, right? Okay, I'll present this later on. So let's address your question. Yes. So yeah, you can combine them in the load combinations. Yes. Yeah, you can combine both of them in the load combinations. Yeah. The other one is if you have buried or partially buried. Explosives. Some analytical expressions. Things that let's say if V is what we call as the PPV or the peak particle velocity. For Z values less than 5 meters per kg cubed, kg 1 power 3. You can calculate, so this is a buried structure and you have a buried or even a partially buried explosive. So it's going to induce, the peak velocities are going to induce a PSO on the structure. So you can calculate, there are expressions. So PSO is rho times CU, where U is given as, it also depends on the soil, but the soil is accounted for by the wave velocity C. U is given as 48 F C, it's a multiplied by 2.52 R. Again, expressions and the form of the expressions, what you can get is what I am trying to present, minus N inches per second. I am sorry, meters per second. Some of these are in response to questions you have asked. I had not originally planned actually some of, especially these two topics, but there were several questions, so I thought I'll address them. Where rho, let's start, what's that? Minus N. C is the, this is an attenuation coefficient. I'll address all of that. It is the wave velocity in the medium. Now you are seeing different parameters that come into play. The density of the soil, W is the weight in kilograms, F sub C is a dimensionless coupling factor. And this is 1.0 for fully coupled systems. When you say fully coupled, it basically means fully buried. I can later, maybe I do not have this. The coupling factors look something like this. This is F sub C. It is a function of the distance from the system D by W power scaled distance, basically D W or cube root of, let me be a little more clear there, D divided by cube root of W, and this is F sub C. So, if the medium is concrete, it will look, this is 1.0. It looks something like this. Wait, let me take a, so it is more, starts at about 0.6, this is minus 0.1, that is just, and here it goes up to 0.6. If it is soil, regular soil, from 0.2 it goes up to, this is soil coupling factor, and then air, the coupling factor there is 0.2. So, you have the coupling factor, we have the R, W, what is that? Minus N. I am coming to that, yeah. So, N is that what your question was? What is N? So, N is a dimensionless attenuation coefficient. Can't seem to spell today. Dimensionless attenuation coefficient. I'll talk about N in a moment. Which one? D is the distance. Yeah. So, yeah, depth R, D is the depth of the barrier, right? More D, the D, oh yeah. So, R is the distance, maybe we can draw that picture here. Okay. Thank you for asking that question. So, we have addressed N, I am coming to N, there is, okay, might as well talk about it now. It was a little ahead on my notes, but N is 1.5 for saturated clay to varying up to 3.25 for very loose sand. And if you are interested, I can get you a table that gives you for other types of soils. So, F here is 1.0 for deeply buried explosive. The other thing of interest is our specific side-on specific impulse. The side-on specific impulse IS is again rho C V. V is the peak particle velocity. V is given as an expression 60.8 W power 1 over 3 Fc over C 2.25 2.52 R by 1 W power 1 over 3 1 minus n. And C is the loading wave velocity. There are further differences. C is equal to small c for fully saturated soils, and there are expressions, I will just mention it anyway for completeness, C plus n minus 1 by n minus 2 U for sand and 0.6 C plus n plus 1 by n plus 2 n minus 2 sorry U for clays. So, for instance, consider weight of 27 kgs at R equal to 10 meters and depth equal to 9 meters. C is 500 meters per second. Question is, calculate PSO. You can calculate the impulse also, but calculate the PSO value. So, we start with U is 48 Fc. So, F sub C divided by, not divided, multiplied by 2.52 R divided by 1 over 3 R minus n comes to 48 multiplied by F coupling factor, let's say, is 1. If you come over here, here it is up to 0.6. So, d by square root of w, cube root of w is 9 divided by cube root of 27. So, the coupling factor is 1 multiplied by 2.52 10 meters divided by minus n depends on the soil. We talked about from 1.5 to 3.25. So, if it is saturated clay, I have taken it for this type of soil. So, this is minus 1.5 comes to 2 meters. So, PSO is 2 multiplied by 1500, rho is 1500 kg per meter cubed. So, this is rho Cu multiplied by 500 meters per second. So, rho C and U comes to 1.5 into 10 power 6 pascals, or PSO is 1.5. Can be a, so I get this number unless I have made a calculation mistake anywhere. So that's a little bit about, and you can explore more on such topics. Yesterday I think, and you can talk to Professor Argappan about this, penetration is another impact. We have seen you can use, there are expressions for different types of materials, wood and other such things. I can present one, but it's not really needed. These are also there. Now, I think in UFC, if you're interested for penetration effects due to direct fire weapons, you have a UFC 4-023-. Several examples are presented for different types of materials. You can calculate, for instance, you have the bullet coming in with a velocity and a mass m. You can calculate the thickness that is required, expressions for as it comes out, this is VR. So, you have expressions for TW, VR, etc. These are the two main things you would be interested in. So, so that is a little bit about, to address again one of the questions that has come about. You can at least start looking into those effects. It's about 10 minutes to go. Maybe one more thing and we'll talk about, we should be able to do that in the next session, right? That any does. Okay, okay. But I'll give an idea of advanced analyses. So, the analysis type Of course, the first is analytical expressions. We've spent a lot of time on analytical expressions which can give a base or a ground reference. Then, based on analytical expressions, we've also done equivalent single degree of analysis. We've used nonlin for this purpose. You can develop your own. All you need is a good integration. You can Newmark integration technique, implementation of it. You can develop your own and expand on it, or use nonlin. There are others as well. If you search, you may be able to find. And then the third thing is, even yesterday, I don't know, I was having a discussion with somebody, and then for that also equivalent SDO of analysis, all you have to do, foundations on springs, for example. You may not have a equivalent equation for, let's say you're applying this, you know this is PL cubed by 48 EI, and you know delta is equal to, your K is equal to 48 EI by L cubed. So, you have analytical expressions for it. But if you do not have analytical expressions, you can model the system. So, you can model, you can do an elastic model in finite elements and then find whatever. If you're modeling, you can model springs and then find the displacement, and then you know the stiffness is force divided by your displacement. So, you can model, that's an alternate way to get your stiffness for single degree of freedom systems. Then the third is advanced finite element analysis, or the fourth one, advanced finite element analysis. There are many programs. You have to ideally, before you use some of them, some of the background courses recommended, of course, it's not possible to do it, is elasticity, theory of elasticity, plasticity, especially this is for understanding the extent and limitations of material behavior. This gives you a extents and the limitations of material behavior. You can use Google and find model parameters and substitute, but then you're shooting in the dark. Even sometimes I've done these courses, but I'm also shooting in the dark at times because I really don't have a physical feel. I know mass, what it is, but then I look at some of these parameters, I understand the complexities of the model and the implementation of these models in a numerical systems, I understand those things. But then what do these parameters use? What is the sensitivity of the parameters? If I have 10 parameters, am I supposed to test the sensitivity of all those 10 parameters? How do I independently determine the values of those parameters? All those things are up in the air. Then of course, you can do 2 or 3 courses in finite element analysis. I have done the basic one, numerical, mathematical ones, advanced nonlinear finite element. A lot of these are nonlinear finite element analysis. So, course in continuum mechanics, all these are part of understanding, part of the behavior. And of course, this course in blast analysis gives you the application side. This can be applied to many things. Yesterday, modeling the behavior of that hole in that plate. All these background courses are important in, well, once you get into that, you have, understand that you have programs available for you. You have the one that you're going to use this afternoon, Abacus. I've used Abacus too. Abacus has limited material models. Limited, especially for concrete. Abacus, especially with explicit, there's implicit and explicit. Explicit is the I forgot to include numerical techniques. Numerical methods, advanced numerical methods, where you learn about implicit integration techniques, explicit integration, or it could be part of other continuum mechanics or finite element analysis courses. So, limited material models, but it does do it. So, I use LS Dyna, which has got a wide range of, I work with still concrete, so wide range of soil and concrete and metal composite material models. You can develop your own. People have developed literally hundreds of material models. So, it's got, the other thing is the types of analysis.